Now let's suppose that instead of calculating input impedance from a known transmission line characteristic impedance and known load, that instead we want to calculate a known load impedance if we know the input impedance and characteristic impedance of the transmission line. And to do that, we can use the Smith chart again, but instead of using this wavelength towards the generator scale, we're going to use the inner scale here, which is wavelength towards the load. Just like the wavelength towards the generator scale, it's also gradiated in units of lambda, so whatever the length of the transmission line is in units of lambda. But however, instead of rotating clockwise like we did for WTG, the WTL scale rotates counterclockwise. So to calculate a load impedance, if the combined input impedance of the T-line and the load are known, the first thing that you want to do is calculate normalized input impedance. So lowercase zn is just equal to capital Zn divided by capital Z0. So that's going to give you your normalized input impedance. You then draw that point on the Smith chart and you draw your operating circle. You then, so let's just kind of fake that. So we've got a Smith chart, we draw Zn, we draw the operating circle, we then draw the line from the center of the Smith chart through the normalized input impedance, and we notice what the WTL scale is in this case. So we then rotate that line counterclockwise, whatever the length of the transmission line is in lambda WTL, and then we find that out on the scale, and then we plot this line here, and we find out where that intersects, and that's going to be normalized, sorry, not Z0, it's going to be the normalized load impedance. So that point of intersection is going to be the normalized load impedance. And just like the last slide, I feel like it's easiest to do this using an example. So here we want to determine the load impedance of a circuit with a line of 0.67 lambda and a characteristic impedance of 300 ohms if we have a combined input impedance of 450 minus J150. So the first thing we're going to do is calculate the normalized input impedance. So that's just going to be the input impedance 450 minus J150 ohms. We're going to divide that by the characteristic impedance, which in this case was 300 ohms. And that gives me 1.5 minus J 0.5. That's my normalized input impedance. So on this Smith chart, I just draw that dot right there. The next thing I do is I draw my operating circle. So I take my compass and I draw my operating circle using my compass. Then what I do is I draw a line from the center of the Smith chart passing through the normalized input impedance point, and I go all the way out through the Smith chart. And what I look for is this intersection right there, and I read the inner side of that scale, and I write down what the wavelengths towards the load is. In this case, if you're following along, it's 0.2026 is the value that I'm reading from right there. The length of the transmission line is 0.67, so what I want to do is I want to rotate 0.2026 plus 0.67, and I notice that this is going to be larger than 0.5, so now I need to minus 0.5 lambda, because remember, every full rotation is a half lambda, and so that is equal to 0.3726 wavelengths towards the load. So what I then do is I go from this point, and remember, since I'm doing WTL, I need to rotate counterclockwise. I rotate counterclockwise, a total distance in this direction, which is a rotation of 0.17 lambda, and that gets me to my point, 0.326 lambda. That's right here. I'm reading it off the inner scale. And then what I do is I draw a line from the center of the Smith chart to this point right here, so I draw that line, and then I find out where that line intersects with the operating circle, and I write Z load is equal to whatever the point is right there, and it's 0.87 plus J 0.52. So now all I need to do is unnormalize, so capital ZL is just equal to lowercase zl times capital Z0, so that's 300
times 0.87 plus J 0.52. So that gives me a load impedance of 261 ohms plus J 156 ohms. And so that's how to calculate an input impedance using the Smith chart.